in the previous class, we had taken up one small point for discussion, which is the graphical representation of sound waves, and that kind of works something like this. So if you have the displacement of the particles in the medium along the y-axis, this being the mean position.
Can you make the font a bit bigger?
Font? I'm using a whiteboard marker. It's appearing too small. Are you using a desktop or a laptop screen? Then
Laptop.
Yeah, so I just wanted to check one thing. If you have the screen open on, and I'm telling this generally to everybody, if you have it on gallery view, so you're also able to look at all your friends, it's not going to work out very well. What you should do is the screen that I am using.
I have pinned your video.
I just pin the video. So when you pin the video, then it appears. You might be doing this already, but I just thought I want to check. And of course, it won't work at all if you are using a mobile phone screen. This writing is appearing too small, is it? Is that what you want me to correct?
Yeah.
Okay, okay. So, but that's displacement, I've told you already, so I'm not going to change that right now, I'll carry on. And if you have the distance in the x-axis, the distance moved by the wave, then I was telling you that the displacement will increase to a maximum value and then decrease to a minimum value, right? And this process will continue, okay? The maximum value that the wave displaces to and the minimum value that, sorry, not the wave, the particle displaces to, in an ideal situation where you have very nicely behaved sound waves, which means that the particles are displaced equally about its mean position, then you have a pure waveform, okay? Rarely, if ever, does that happen. You can generate it electronically, a pure waveform. I'll show you how that is done using this Audacity. But even in that, it's not so pure. So even if you use a tuning fork, it's not going to be as pure as theoretically it can be. Then I was telling you that this is a way in which we can represent sound waves, where the displacement from the mean position becomes the amplitude of the wave, the distance, this distance from one mean position to the next mean position, node to node as we say it in mechanical waves, or from the crest to the crest or trough to the next trough, that distance will be your wavelength. And if you have a timestamp, that is, if you know in what time frame this is happening. So let's say that it goes from here to here in 1 second, then you can also say what is the frequency. So the frequency, if the time period happens to be 1 second, then the frequency will be 1 hertz. So these kinds of information can be interpreted straight away from this. The reason why I'm repeating it is that this kind of a question is a question that is quite often asked in the board paper. At least every alternative year they ask a question based on interpretation of the waves. It's easy to score marks in here. So you should, if you know what the different parts are, then you should be able to answer any question that they ask. The typical kind of question that they will ask is that if there are two waves that are represented like this, okay, with the orange wave having the label A and the black one having the label B, what is the difference between, what are the similarities and what are the differences? Let's say they ask you this question. So can you name one similarity and one difference between A and B? Anybody can answer.
The wavelength is the same.
Yeah.
The wavelengths are the same, but their amplitude is not.
Yeah, so you can say that the differences are, the difference is that the amplitudes of wave A and B are not the same, but the wavelengths, so the similarity would be that the wavelength is the same. If the time frame is given, if the time period is given, you should also be able to say that the frequency is also similar. So they may say out of frequency, wavelength and amplitude, which of these are similar and which of these are dissimilar. 3 mark question straight away. Okay, so easy peasy, you should be able to score the marks for this. um, One, is that clear to everybody? Did everybody get the point? If you want me to,
Yes.
if anybody
Yeah.
wants me to repeat it and you didn't kind of get it, I can repeat the point.
Repeat it, sir.
Can you repeat?
Yeah.
Yeah.
The second type of question, I'm just imagining different kinds of questions that can be asked. Basically, if you know what is fundamentally being represented over here, it should be possible for you to answer any kind of question. So my question was, out of wavelength, frequency, and amplitude, the question could be, which ones are similar for waves A and B, and which ones are dissimilar for waves A and B? 3 mark question, because you have been asked to compare three things. It will be a 3 mark question. So it's going to be straightforward for you to score these marks. All you have to say is that the time period is the same, so therefore the frequency will be the same for A and B. The distance that the energy travels in the x-axis is the same for A and B, so therefore the wavelengths are similar, and the amplitudes are different because the mean position, the displacement of the particles about the mean position is different for A and B. So therefore, A has a lesser amplitude than B. Another kind of question could be, which one has the greater amplitude, A or B? Again, read the question carefully and answer it appropriately. The marks are there for the taking. Another kind of a question that can be asked in this is, let's say that there is a wave which is shown like this. It's a very small amount of space, so I'm just going to, I hope you're able to see the blue colored wave, and let's say we mark that as wave C. Are you able to see the blue colored wave clearly?
Yeah.
Yes.
Yeah, strictly speaking, I shouldn't be calling it a wave. It's a representation. It's a graphical representation of the wave. It is just unfortunate that it kind of looks like, the wave itself, the mechanical wave itself, but we are representing sound waves. So wave C, if you were to compare with, let's say, wave A, all right. So compare A and C. For wavelength, frequency, and amplitude. Okay, now anybody can answer that. So somebody answer it for wavelength, somebody answer it for frequency, and somebody answer it for amplitude.
Amplitude is the same for both of them.
Yeah, amplitude is the same. I have to sort of draw it a little more accurately to show the amplitude being the same. It should touch the maximum line. They will draw it appropriately. But yes, you're right. My intention was that the amplitudes for wave, wait a minute, A and C, not B and C, but Sonia.
Oh, right. Right. Sorry.
Yeah, I think you just made a mistake looking at the signs, but I meant A and C. So for A and C, are the amplitudes the same?
No. No.
No. Which has the higher amplitude?
C.
C.
Out of A and C, that is. C.
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 Can somebody tell me something about the wavelength?
It's half. The C
Wavelength
wavelength is half of A.
is half.
The wavelength is seemingly half. That is, if we assume that these two distances are the same, then the wavelength is half. Which one has the lower wavelength incidentally?
C.
C.
And therefore, what about the frequency?
It's double of A.
The frequency is therefore double of A. And that's straightforward from the wave equation, right? V is equal to F times lambda. So therefore, assuming that the velocity of this is, because it's sound, it will be constant. If the wavelength decreases by half, then the frequency will double. Okay, so that's how you do the interpretation. They rarely ask you to give an explanation for your answer, but of course if you know the fundamental principles correctly, then it should be easy for you to also give the arguments. It only means that you write more marks, you get more marks for that. So to say whether this is more or that is more, you get 1 mark, and to give a reason why it is so, you will get another mark. So make sure that you are able to put your arguments correctly. Okay, let me just check. I have this year's question paper. It just happened to be in my textbook. I just see if there is a question about waveform somewhere over here. If there is, then we can pick it up. Nope, there's nothing about sound over here, so bunk that for the time being. So I think that kind of wraps up whatever we needed to know in terms of interpretation of graphical representation of waves and the kinds of questions that will be asked in this. So we can move on to the next section, which will be about applications of waves.